So the last class we were looking at the effect of pressure on the flame speed, and what we found was for a nth order reaction, for let us say a global reaction, the flame speed goes as p to the n over 2 n minus 2 over 2, and this basically gives a weak pressure dependence for typical hydrocarbon oxidation combustion reactions with a order close to 2, a global order to close to 2. So for typically second order reactions. Then there are lots of other parameters that we have to think about, or variables. Of course, when we talk about pressure, the next thing we obviously think about is the effect of initial temperature. So or rather than saying initial temperature as if it's an unsteady problem, and in a steady state situation we should be thinking about like a effectively temperatures of the unburnt reactants, okay, or far upstream reactants. So temperature, effect of temperature, reactant temperature. T naught. And now of course these things are more like information, so you can actually gather these things from most textbooks. We will just go through this rather quickly to highlight what the most important aspects are, and it's also important to think about this in physical terms other than just to look at explanations. So what we are saying here is, as far as T naught is concerned, okay, the gross effect is like if you now say SL, that goes as T naught to the m, let us say, where m is around 1.5 to 2. So if you think about this, if you now look at SL versus T naught, you get graphs that go kind of like that, right? So why is this? This is mainly a preheating effect, okay. So because what you're thinking about is you have the reactants that are approaching the flame in a flame fixed coordinate system, and then you have the preheat zone, and the temperature has to now rise from there up to the reaction temperature in the reaction zone. So this effect is primarily a preheating effect. Alright. So if you were to be thinking about like a PhD qualifiers question, the question will not be what happens to the flame speed with the reactant temperature. The question would be what happens to the flame thickness with reaction the reactant temperature, right? So we'll ask this question differently than what's normally done in the class. So that's for you to think about, okay. So we say it's essentially a preheating effect. Now the other thing that you naturally have to think about when you're looking at the effect of anything on flame speed is what is the effect on the reaction rate, because you see that the flame speed is directly proportional to square root of the reaction rate, right? So as a matter of fact we got this n minus 2 over 2 for the pressure because the reaction rate was going as p to the n, and then since the flame speed is proportional to square root of w, you have a n over 2, and then of course you had a 1 over density in the as a factor out, so which was linear in pressure, therefore you had this n over 2 minus 1, that's how you got this. So the first thing that you have to think about is the reaction rate. What is the effect of whatever parameter you're thinking about on the reaction rate, and therefore on the flame speed. This is the first step approach. The next thing that you have to think about is what does the reaction rate itself depend on, and it primarily depends on the flame temperature, right? So what is the effect of anything on the flame temperature, and through that on the reaction rate, and through that on the flame speed. This is how we have to look at this relationship. That's very important most of the time, but in this case T naught of course affects Tf directly, and then Tf affects W and W affects SL, but in this case you know the Tf effect is significant, right. When compared to the Tf effect, the influence that T naught has on the Tf and therefore on the SL is marginal. So this rise is primarily directly because of the preheating effect and much less through the effect through Tf. So the influence through Tf is less here. If you now look at how the Tf itself affects SL, that's the next thing that we should look at, effect of flame temperature Tf on SL of course is significant. So here what you will find is these curves are much steeper. So if you now look at Tf, this is of course like we are essentially looking at different mixtures having different Tfs and what happens to the SL corresponding to that, keeping lots of other things constant. So it's a bit difficult to actually think about this experiment, but if you now think about this curve is much steeper when compared to this. Okay, so a slight change in Tf can cause a significant change in SL. Through W, that is the reaction rate. So now if you go back and think about this, the first thing that we did was when we wanted to look at the structure of the premix flame, we said the reactants get in and then the temperature rises and then goes to the reaction zone. But if you want to just do a gross order of magnitude balance, we would say the reaction rate is evaluated at the flame temperature, right. We don't have to worry about the variation of the reaction rate with temperature, we will just evaluate the reaction rate at the flame temperature directly, and this justifies that because as Tf changes, W changes, and as W changes, SL changes. There is a direct link between these things. So we can see this justified experimentally. Then the most important thing that we should be looking at most of the time, effect of mixture ratio. So when you say mixture, we are always looking at the reactant mixture. Okay, in the context of premix flames, we are always thinking about the reactant mixture, that means the fuel oxidizer mixture, right. So here what happens is SL versus let's say equivalence ratio, and of course you can think about equivalence ratio 1 as stoichiometric, and then less than 1 is fuel lean, greater than 1 is fuel rich. You should typically look forward to curves that are like that with a peak little bit off in the fuel rich region. Okay, so peak nearly at stoichiometric condition or slightly fuel rich. Right. Now just to also give you some numbers, we are talking about laminar flame speed, so we are looking at these things measured typically in centimeters per second, and these are about let's say 10, 20, 30, 40. These numbers would probably work for methane. Lots of other fuels will give you these kinds of curves at much higher values, maybe not much higher, maybe twice as much or maybe 3 times as much or so, around that. So we are talking about a few to several tens of meters per second, sorry, a few to several tens of centimeters per second for the laminar flame speed. Okay, so this is something that you got to keep in your mind, and in order to get a feel for things when you do, let's say, experiments or even numerical work and so on. Now the other thing that we have to worry about is why are we having a peak that is slightly shifted off. The reason for this is actually again through TF. So look at how the variation happens for the TF with respect to equivalence ratio, right. You will find that it peaks up near the stoichiometric condition or maybe slightly fuel rich again, and that is because of the CP effect. That is the CP, if you now look at how the CP of the mixture varies with phi, right, you will find that the CP affects the TF, and then on top of it, think about this, TF is actually sitting in W, and on top of, and then there is an explicit CP dependence directly on for SL. Okay, so the CP influences TF and CP directly also influences SL. Therefore you will find a further slight shift into the fuel rich region because of this reason. So this is again mimicking TF trend and a further CP effect. We will look at the CP effect directly right away. That means we want to keep the TF constant and see if we can vary the CP or so, that kind of thing. So let's just see how that can be done. So effect of alpha and CP, right. I want to just go back and point out something here in this picture. So this curve stops on either side beyond a point as you go from go away from equivalence ratio 1, and this would be the fuel lean flammability limit, and this would be the fuel rich flammability limit. That means if you now have too much of either fuel or oxidizer, the flame is not going to propagate, and that's called the flammability limit, and we will talk about flammability limits separately later on, but we have to keep this in mind that this curve is going to actually hold only over a range of phi around 1, significantly around 1, it's not like just around 1, but not too far away on either side. Okay. So going back to the effect of alpha and CP, alpha is of course the thermal diffusivity. So the way we can actually think about this is also pretty interesting. So you can now think about SL and versus phi. If you now look at let's say CH4 in air, right, consider various oxidizer inert mixtures, right. So that is like O2 N2 as in air, and O2 argon and O2 helium, all in the same proportions. Okay, so keep the proportions the same, you should now get pictures that look like that, and this is for N2 with oxygen, this is for argon, and this is for helium. So question is why are we getting this? We can think about it in multiple steps. The first thing that we want to think about is this combination. Both of them are inert gases and monatomic. Okay, so when you say they are monatomic, then their CPs are nearly the same. right, and the only thing that's different then is the density, therefore the alpha changes. So Cp doesn't change but the alpha changes. So if you look at how the SL behaves, SL is like 1 over rho naught square root of Kw divided by Cp. These are the dependencies. So K over rho Cp is what we are looking for as alpha. So you should now be able to write K over Cp explicitly in terms of alpha, and then you should be able to look at an alpha effect versus a Cp effect separately. That's what we are trying to do. So what you're saying here is, because the helium is lighter than argon for the same Cp, alpha of helium is much larger than for argon. Than for Ar, and then what happens is, you can fix your flame temperature, all right. That means you can get your flame temperatures to be the same because the Cp is the same. So flame temperature depends primarily on Cp as far as this is concerned. So for the same flame temperature, higher alpha means higher SL, all right. So that is the reason why you're going to get a helium diluted SL to be having a higher value when compared to argon diluted flame speed. Now then, what happens to this combination? What you have to think about is, here the Cp's are different. Okay, so between argon and nitrogen, this is a monatomic gas, but this is a diatomic gas. So therefore the Cp is different. Now N2 has a higher Cp, being diatomic, okay, relative to argon. Argon is a good comparison with N2 because the alphas are nearly the same, okay, for same alpha. So that way you can fix your alpha somewhat, and then say look at the Cp effect. Then what happens is SL with N2 then becomes lower than SL with argon, right. But then when you are thinking about change in Cp, right, we started thinking about change in Cp even here when we were talking about the SL variation with phi following a TF variation with phi trend, and then we were thinking about why was the TF actually varying like that, and that we argued it through Cp of the mixture as the phi is varied, and therefore there was this trend that is shifting towards the fuel rich side. So similarly Cp is now going to directly affect the flame temperature, all right. So here what happens is TF also depends on Cp. So here in the case of SL varies through W and TF, and therefore Cp effect there, and then an explicit Cp dependence in the denominator. Therefore you now have a double effect, both of them actually adding up together. So what happens is, typically this gap is larger when compared to this gap, because you now have both the Cp influencing TF and then Cp influencing directly, okay. So TF also depends on Cp, and it also affects SL. So keep that in mind. And then there are some more interesting things that we should be thinking about. Before we proceed, this is a very interesting thing as an experiment for you to do. and we will shortly talk about like a Bunsen burner flame stabilization. Alright, so we will look at what's the condition for flame stabilization in a Bunsen burner, for example, and then we will say okay, now I'm going to have like a methane air mixture that is burning in a Bunsen flame, and then I slowly shut off my nitrogen in the air and then try to introduce argon, and then I progressively shut off the argon and then try to introduce helium. Okay, so what happens to flame stabilization? So this is like a trick question that is typically asked in like qualifiers or exams, right? So we don't necessarily ask you directly about this, that's like kind of reproducing what's there in the textbook, right? But we also try to couple this with the flame stabilization issue, rig up an experiment where we can vary the diluent type from nitrogen to argon to helium and ask progressively what happens to the flame shape in a Bunsen flame, and look at its stabilization and so on. So effectively we are playing with the SL while we're trying to do that in relation to like the flames with the flow speed. We will talk about that later on, so keep this in mind. Proceeding with chemical effects, so effect of molecular structure of fuel. Typically fuel is what's of interest. The oxidizer is always air most of the time in what you're talking about, or at least oxygen with any diluent. Now what we find is two things we have to think about. One, more unsaturated hydrocarbon, higher is SL, and saturated means you have like double bonds and triple bonds, right? So it's not like alkanes, we are now talking about alkenes, alkynes, those kinds of things. They would have typically much higher SL when compared to when you only have single bonds. Then the other thing that we should think about is substituting methyl groups for hydrogen, right, leads to SL decrease. That means, like for example, when you now have methane, you have 4 hydrogen atoms, right? So instead of that, you now say take one of the hydrogens and then you have CH3 that becomes ethane, right? And then you can now have like CHCl3 or CCl, CH3 twice, and then CH3 thrice. So you can progressively replace your hydrogen atoms by methyl groups and then form larger molecules with more carbon atoms and correspondingly hydrogen atoms as well in the methyl groups. What this can lead to is two things. One, it implicitly also increases the number of carbon atoms. Okay, so if you now directly look at what happens to the SL as a function of number of carbon atoms, right, what you have to do is look at straight chain hydrocarbons like methane, ethane, propane, butane, pentane, and so on. All of them N, from propane onwards you have to think about like N propane and or N butane, N pentane, and so on, right? From butane onwards you have to think about like straight chains. The other way is like if you now take a methane and then start attaching methyl groups, progressively you now begin to get, like for the butane it doesn't have to be N butane, it could be like an isobutane. That means like you have a branched methyl group. Even if you have straight chains, as the number of carbon atoms increase the flame speed decreases, provided we are talking about alkenes and alkynes. In the case of alkanes there is hardly much of an effect. So if you now look at the number of carbon atoms You can look at like a curve that looks like this for alkanes, a curve that looks like this for alkenes, and a curve that looks like that for alkynes. And these numbers are pretty interesting. So this is like centimeters per second. Like for example, you would have something like 50, 100, 150, 200, and 250, and so on. Keeps, you see this. Now of course when you're now talking about alkynes, you're looking at a triple bond, so obviously you need to have at least two carbon atoms for a triple bond to be formed in between. So this is like acetylene, and you can see that acetylene has a very high flame speed for two reasons. One, the number of carbon atoms is less, and it is unsaturated, it's highly unsaturated. So both of them contribute to a high flame speed. So 3 is number of carbon atoms leads to SL decrease more with an unsaturated. And one more thing that you have to think about is when you now have a increase in the number of carbon atoms, there is a molecular weight effect that's coming in. Okay, so additional effect is fuel molecular weight. Fuel molecular weight, right? And so this actually influences your alpha for the mixture, and through that you also, so one thing is the reactivity, right? So that means it affects the reaction rates. The other thing is the molecules are getting heavier and heavier, so it influences your alpha, and from there you're beginning to get an effect on the SL. So these two things compound and makes, for example, acetylene to be highly reactive. So that's the reason why people say if you're working with something like an oxyacetylene torch, like in welding applications and so on, you got to be a bit careful. I shouldn't say a bit careful, maybe quite careful okay, on safety considerations, because it is highly reactive. And in fact I should point out that here we are not looking at a TF effect, TF note, TF, and as a matter of fact even the activation energies for, like, let's say global reactions of oxidation of most of these fields are comparable, right? So this is not necessarily like a TF effect at all. So then the other last point that I would like to make is about chemical reactivity. So a good comparison that is made is, for example, if you now have a silicon hydrogen bond versus silicon carbon bond, like SiH4 similar to CH4, right? SiH4 would probably have like a large reaction, what do you call, flame speed. Okay, so this is because this bond is actually quite reactive when compared to, let's say for example, if you now progressively replaced the carbon atoms in methane with silicon, right, and you go all the way to having SiH4 versus, you can say, I'm sorry, SiCH3 H2 and so on. So if you now have some such thing, that would be less reactive. So if you now have like a silicon carbon bond, that's going to be less reactive when compared to silicon hydrogen bond. So these are things that you can pick up from textbooks, not very difficult, but what you have to keep in mind is to highlight 2 or 3 things. One, have a feel for numbers. Okay, we are talking about tens or few tens to several tens typically for most flame speeds in terms of centimeters per second. You You can also look at some of these having a few hundreds of centimeters per second. That's one thing. The second thing, always look for the effect of any of these things through TF, okay, because that's a big effect. There are only a few exceptions. For example, T0, there is a direct effect of preheating, and then there is a direct CP effect that you can think about, and TF does not really influence significantly when you are thinking about different fuels with different carbon chains. So there is a molecular effect and so on that's coming to picture. So some of these are exceptional, but most of the time whatever TF does with whatever parameter they are thinking about, SL would try to follow that mostly. So and then keep this shape in mind, this, and then of course what happens when you now progressively dilute it with different gases of different monatomic or diatomic gases, and then also when you have different molecular weights or densities and so on. So this is pretty interesting as well. Now with this, what we should now try to do is a slightly different framework. Once we now know how to deal with how to get the flame speed, then how do we deal with premix flames? So then we talk about what's called as the G equation. So what happens when you're thinking about a G equation is when the flame is much thinner than the hydrodynamic length scale, of the flow, right? We can treat this flame as like a surface surface that is propagating in the flow. So it is essentially like a surface of discontinuity. The flame can be treated as a surface of discontinuity, right, propagating in the flow. That means the flame has a certain propagation speed which we now kind of take for granted. We have gone through enough of what's happening across the flame, within the flame, how the temperatures rise, the concentrations fall for the reactants, lots of things, and then we now have the preheat zone, the reaction zone. We could have like multiple preheat zones for non-unity Lewis numbers depending upon diffusion length scale versus conduction length scale. Lots of such things we have thought about, right? And then we have also further thought about what are the effects of pressure, temperature, flame temperature, all these things. But now let's say flame speed is given, right? If the flame speed is given and you are now talking about a situation where the characteristic length scale of your flow is much larger when compared to the flame thickness, okay, and the flame isn't very thick many times. A laminar flame, for example, is very thin, right? It's about a few millimeters thick. Of course it is much, it's quite thicker than a shock. Like if you're thinking about gas dynamic shock, that's only a few mean free parts thick, okay. You have a sudden change in properties across a very small distance, where even continuum assumptions are broken down, whereas that's not the case with flames, but still it is quite thin when compared to most applications, where you come across most applications. Therefore if you now think about this, you now say that's a flame which is now beginning, which is trying to propagate into a flow, right? Now where was all the preheat zone and all those things? It's kind of like you now have to take a magnifying glass, hold it against this, right, and then that's going to kind of look like and so on, all the stuff that we drew. and so it's almost like locally one dimensional. So when you now say locally one dimensional, that means the flame is trying to propagate with its flame speed normal to itself, right. So the flame could be curved, that refers to the flame shape, whereas what we have been talking about so far is what is called as the flame structure. A flame shape is like a much global picture. A flame structure is something that happens almost like at a point in the flame, along the length of the flame, right, where you now try to spatially resolve temperature and concentration profiles, reaction rate profiles, all those things across the thickness of that flame. So what we are talking about is locally normal to itself, it's going to have a flame speed, which is now of course going to be in different directions. Flame speed is a scalar, right, and it depends mainly on reactant temperatures, pressure, reactant temperature, pressure, and the mixture ratio, all right, and all the other parameters, like what is the alpha, what is the Cp, and what are the kinetic constants, what is the order of the reaction, all these things, right. So once all those things are given, if you are given a certain mixture at a particular ratio and temperature and pressure, SL is fixed as a scalar. The flame speed acquires a direction locally normal to the flame shape. So dependent upon the shape of the flame is how the flame propagation direction is fixed. And many times you would think, wait a minute, the flame is probably going to shape itself depending upon how it can propagate, right, and I will have to try to find the shape in the first place depending upon how it can propagate. If I don't know how it is going to propagate, how can I figure out what its shape is, and how can I figure out the propagation direction? So it's a loop that we have to think about. So how do you do this, right? So the way we deal with this situation is, we now say this is actually treated as a surface of discontinuity, and we want to mathematically describe the surface by a by an equation called g of x vector comma t is equal to 0, right. So the geometry of the surface can be represented as g of x vector comma t equal to 0, x vector referring to the position vector for that particular position there. Now if you are trying to do this analytically, you could just deal with this surface having this equation, right, as it is, or the other possibility is you can now think of g as a scalar like enthalpy or temperature or anything, okay, just like any scalar. So it's sort of like if you now have, and particularly what's called as a passive scalar, that means a scalar that does not influence the flow, okay. So if you now kind of have a scalar quantity that is actually dropped in the flow, it just goes with the flow, right, unless it has a propagation speed that it wants to compete with the flow against, right. So that's the kind of thing that we want to see. So if you want to look at it as a scalar, that means it's a scalar field, that means it should be defined and described everywhere in your flow field, right. So if you want to do that, then there is a way of dealing with this, that is, you can say g less than 0 could refer to the unburned state, and g greater than 0 could refer to the burned state. That means all reactants have a value. The reactant field now should be assigned a value of g that is less than 0, and the product field should be assigned a value of g that is greater than 0. And what happens in the entire field as you now solve for g is the g rapidly rises across 0 within a very thin narrow region. mathematically speaking it's almost instantaneously happening, that's why it's a surface of discontinuity at the flame, alright. That means it's having a value that's less than 0 up to the flame, it's now suddenly jumping to a value that's greater than 0 on the other side. Numerically, like if you want to now do like computation, like right, okay, discretized approximate numerical calculations, you could now think about some values from let's say -1 to +1 and look for a contour or a surface where typically when you discretize your space over maybe about 2 or 3 grid points you now have a sudden rise in G, right. So that is like a approximate way of doing the flame, but effectively we are looking at something like this. So what you want to do is as I said, SL itself is scalar, so it acquires the direction normal to the flame, therefore you need to actually define a unit normal vector. Unit normal vector, we are of course assuming the flame surface to be continuous and smooth, alright. That means so it is important to actually have a continuous and smooth flame as an assumption, because at every point you need to be able to define a unit normal. So if it is not smooth and it's kind of having like a cusp, then you're going to have multiple unit normals at that point which is ill defined, right. So you can't really allow for cusps to happen, so that is like saying it is really not smooth but it's still continuous. But there are situations when actually the flame gets cut, right. But even when the flame gets cut it actually tries to coil around and then make like a circle and then start consuming reactants that are entrapped within this zone. So momentarily you might find some discontinuities, but pretty soon you're going to get something to be made continuous. So it's not terribly bad assumption. So what we are saying is, under these kinds of assumptions we now say we can define a local normal like minus grad G divided by mod grad G, and we take n hat as positive when pointed upstream. We need to have a convention on this, and n hat is taken as positive when pointed upstream. Okay, so then what you do is we want to now have an evolution equation for G. How does the G equation evolve, or how does the surface described by G equal to 0 evolve, right. So the evolution equation is obtained by adopting a Lagrangian system. That means you now sit on the flame or you ride the flame. Of course it's going to be pretty hot out there, okay, if you're able to bear that, okay, so you're going to have some fun sitting on the flame, right. What happens as you sit on the flame and it's doing whatever it's doing, you are there. I mean you're not, nothing is happening because you're always sitting on the flame, right. All the fun can be seen only if you now view from outside, like in a laboratory fixed coordinate system you can see the flame movement. So the Lagrangian frame of reference says that on the flame surface, right, dg over dt equal to 0. The reason why we use a ordinary derivative is your space is fixed by the location of the flame. You're on G equal to 0, and the only thing that's varying is time, right. And then we are saying that the G is going to be invariant in time because you're sitting there, nothing is happening while you're sitting there. This in fact is what is typically written as capital G over capital dt in an Eulerian frame of reference. Then with respect to an Eulerian frame of reference, if you now pull yourself out, right, you will now call this the material derivative, right. So this would then mean in an Eulerian frame of reference we have to write this as partial G with respect to time, because G partially changes with respect to time. Besides there is an apparent change with respect to time because of its motion, right. Therefore we have to say capital VF vector dot grad G equal to 0. This is essentially partial d over dt plus v dot del of g. So this is an operator that is acting on g that essentially is basically trying to say, so what is Vf now? Vf is nothing but dx over dt, right? That's essentially the position vector corresponding to where the g is and its change in time. So that means that's essentially the displacement of the points along the flame taken as derivative with respect to time to get the flame motion. So this is actually the local, so this is like local propagation velocity. Right. Now when you say local propagation velocity, it's sort of relative to something that is very local. It's not thinking about a flow field that's around it, it's trying to have a relative motion of the flame with respect to the flow around, right? So this then by definition of the way SL is, right, SL is nothing but the Vf minus the flow velocity v vector evaluated at g equals 0 minus, this corresponds to the upstream reactant velocity at the flame dot n hat. Right. So this is to say that you are going to have a relative velocity between the flame movement and the flow that is manifesting as SL. If your flow were quiescent, right, or if your reactants were quiescent, then you will identically have the flame propagation velocity that we talked about as the flame speed, okay, except we have to now consider the dot product because you have to look at the local normal propagation, right, otherwise you won't get a scalar out of this vector, or you couldn't have made a vector out of the scalar. Either way you can look at this, right. So if you now say so V then is the local flow velocity in lab frame, right, that's the Eulerian frame, and from here we can get, if you now plug this back here, you can get in this equation you can get plus V obtained at g equals 0 minus dot grad g equal to SL mod grad g. That is, substitute for n as minus grad g divided by mod grad g and you should be able to get this, right. So this is what is called as the G equation. The G equation essentially is an evolution equation for the flame surface as if it's a surface of discontinuity across which the temperature changes from the unburnt temperature to the unburnt reactant temperature to the burnt product temperature, and reactant concentrations become 0 for particularly the deficient reactant, and product concentrations go from 0 to whatever is the final product value and so on, okay. We'll stop here at this stage. I'll see you at 3 o'clock tomorrow.